Okay, so we'll get started. All right, so now we'll finish off the discussion on organic chemistry. So main types of organic reaction that you will see over and over would be addition reaction, substitution reaction, and elimination. Here are an example of addition reaction. In this one, right now what I've drawn is an elimination reaction. That means you're removing some atoms. But let's say if the hydroxide actually attack carbon at this position, then that will be a substitution reaction. Okay? Organic chemistry is about understanding the reactivity of each functional group and how can you design experiment so that you can synthesize your target compound without damaging your other functional group. So in organic chemistry, we care about the electron movement because these electron movement is responsible for the formation of chemical bonds. Okay, so when you get into organic chemistry, there will be a lot of mechanism questions to show and demonstrate that you understand how the electron would move around. Okay, so I pick out these two examples because later on you will learn about selectivity. Okay, so there are two possibilities how this compound can react with HCl or how this compound can react with sodium hydroxide. Okay, and then how do we know for sure these are the compound that we end up getting? Okay, so some reaction you will get a mixture. If you do your reaction carefully by controlling the temperature and the concentration, perhaps you can get some selectivity. Okay, so in organic chemistry, besides designing the experiment, it's important that you have technique to characterize the compound that you have. Okay, so now I want you to get in group and talk about how can you use a physical property to determine molecular weight or any kind of substance. How can you use its physical property to characterize it? Okay, so how many of you get melting point and boiling point? Okay, so these are the most basic, and that's what people rely on before they were able to have more advanced characterization technique. Okay, so back in the days, people will measure melting point and boiling point. And generally, these transition point, it's not a fixed number for a lot of organic compounds. Usually, they're within 1 to 3 degrees Celsius. So you will get a range because you're continuously changing the heating rate and when you're doing the melting point. So basically, you just have a instrumentation where you would slowly increase your temperature and then you will observe it through a glass and then see when the solid becomes liquid. Or you can measure its boiling point. Okay, so under normal atmosphere, a lot of boiling points are fixed. But this could be problematic when you get a mixture. Okay, so think about chapter 13. When we mix salt with water, right, it could depress its what? Melting point. It could elevate its boiling point, right? So the presence of impurity or other type of substance will change your melting point and boiling point. So for instance, let's say you have a mixture of water and alcohol. It would be very difficult to measure the composition by simply looking at its boiling point or melting point, right? Because it's really hard to get a very definite answer. Okay, so of course people develop other kind of technique. Okay, so for example, we can treat our compound with different reagent and see what kind of reaction happen, right? So previously we talked about acid and base chemistry. We can do titration and figure out the pKa of our compound. But that only works when you have one kind of acid, right? Because if you have multiple kinds of carboxylic acid, that won't be possible. Okay, so, but you can do reaction with these carboxylic acid or amine or ketone or aldehyde, right? then you can make new compounds. And once you isolate them, you can measure its melting point or boiling point. So that would be an old way of determining what kind of substance you end up getting. Okay, so we can eliminate or the stuff that we don't want by doing extraction. Okay, so maybe one substance is more soluble in water and the other is soluble in organic solvents, then you can do separations. Okay, and how do we know these are the structure that we're getting? So nowadays, so I mentioned Woodward in last lecture. So in the 50s and 60s, people start knowing how to use electronics, right? So then they will start building these instrumentation that we use nowadays. So Woodward used a lot of IR and NMR spectroscopy to characterize organic compound. And we'll talk about it in a little bit. Okay, so IR stands for infrared. NMR, that's nuclear magnetic resonance. Okay, so these are the most two important characterization techniques that can tell you the structure of your chemical compound. Okay, so we know some substances are colored, right? They absorb color because there's what? From a coordination compound, the compound absorbs color because it has a band gap, right? So the electron can get excited and go to the next energy level, and it could emit light if depending on how this electron come back to the ground state, right? Or it emit the excess energy in the form of heat. But infrared, so that when we're talking about color, we're talking about wavelengths between 400 to 700 nanometer. Above this visible range, that's infrared, okay? And previously, we talked about wavelength, right? So we know at a longer wavelength, you go to infrared, but in order for your spectrum to be easily analyzed, at the time, people developed something called wave number, and it's basically just using this equation so that you are not dealing with wavelength, but instead you're dealing with 1 over wavelength. So the typical unit here is used is called 1 over centimeter. Okay, so organic compound, so if you think about a tetrahedral structure, so this is pointing out of the board. So think about this is, let's say this is CH4. Okay, we know these bonds, they can absorb energy, right? And move around, right? So when you shine infrared light on it, at different wavelengths, we can detect what kind of wavelengths can be absorbed by such molecule, right? So you can imagine this bond is not a constant length, like the ball can go in and out, right? So they can do these bending motion, or they can all move around together, right? Or separately. Right? So in the end, when you shine infrared, okay, you put your compound into this instrument, shine infrared light of different wavelengths, and look at how much is being absorbed or how much is being transmitted, you will end up with an IR plot to be something look like this. Okay, so this is just at different wavelengths where it absorbs at. Okay, so let's say you have a pure substance that you already established as identity. There are libraries now that you can just simply put your unknown and compare. So this is just like fingerprint. Every compound will have its distinctive spectrum. Okay, so if they have nearly identical, so the library nowadays can tell you they are 80% right or 90% matching certain compound. So from that, you can kind of have an estimate of what my compound might be. And a lot of time in organic chemical reaction, we're dealing with these addition, substitution, elimination. We're changing the functional group from one to another, right? So each of these functional groups have a special absorption range. Because you already estimate what kind of reaction you're doing, you can already estimate your target product. You can use IR, use the spectrum to figure it out whether the reaction happened or not. Okay, so in organic chemistry, you guys will learn more in depth about how can you correlate the wave number to different functional groups. So let's talk about NMR. okay? I think a lot of you heard of MRI, magnetic resonance imaging. So that's where we can use this very powerful magnet and to determine whether someone may or may not have cancer, right? So MRI is very similar to NMR in its mechanism. I mean, it's called MRI because we really don't want to freak people out with the word nuclear, okay? Even though dealing with very strong magnetic field, okay? So for MRI, it measures water, okay? The water content inside your body. This, I mean, depending on the probe you use, we can measure hydrogen. That's the most common one because these compounds are usually made with hydrogen and carbon, right? So you may wonder, why do I care about magnetic moment, right? Why do I care about the spin? Okay, so these are the fundamental property of these elements. So for example, if I have oxygen 16, there's no unpaired electron, right? There's no extra spin. So setup of nuclear magnetic resonance is not gonna have any signal. So if you think about what an atom looks like, you have electron moving around your nucleus, right? So under a very strong external magnetic field, because these electrons are moving around, they also act like a little magnet, okay? So every chemical compound, they have different electronic configuration, right? So the way it interact with external magnetic field is different. So by this very delicately designed instrumentation, you can end up with, let's talk about protons first. So you will end up these peaks in the NMR, and the unit that's here is commonly seen as part per million, okay? So generally the scale is go from 0 to 12, okay? So the location of peak will tell you what kind of environment, electronic environment are these hydrogen in. So for example, for this double bond, for the sp3 carbon, they're likely to be between 1 to 2, okay? But for the alkene, because it's more electron rich, okay, this is gonna show up at around between 5 to 6. So since we already established where these functional groups would show up, for instance, for carboxylic acid, if you ask me where that H show up, that would be around 10 to 12, okay? And so these are the pattern. You can use IR to confirm what kind of functional group you have, and then you can use NMR to do a double check, because depending on whether this chloral group is located at carbon number 2 versus carbon number 1, the chemical shifts are going to be different. And when you get to more advanced or organic chemistry courses, in proton NMR, it's not just simply one line. So it will have what we call the splitting of the peak. So you could have multiple peak next to your main peak. And that will give you details of how many protons is next to the proton that you're looking at, okay? And then depending on the substituent that you have, they have different chemical splitting frequency. So from there, it will give you more clue of what happened to your reaction. Okay, so we can use NMR to monitor chemical reaction. We can also use IR, but NMR is more sensitive. And let's talk about carbon. So similarly, each of these carbon, they would have different electronic environment, right? So let's say the spectrum of this versus this, they're going to be very different, right? Because this is symmetrical, this is perfectly symmetrical, you're only going to get 2 signals, 2 peaks for this compound, versus here, this is not symmetrical, right? So you're going to get 4 peaks for this compound. So with experience and with literature values, we can really go in and solve for the structure. And there's also more advanced technique is you can run proton NMR and carbon NMR together, or run 2 proton NMR together, so we can do what's so-called 2D NMR. So in 2D NMR, It's gonna tell you which hydrogen is connected to which carbon, okay, by giving you another signal. Nowadays, these are all commercial software package. You just hit a button and you get a spectrum, and then you have to learn how to analyze it. And for the hydrogen-hydrogen couple spectrum, you can also figure out the through space interaction. So usually for a typical 1D NMR, we only look at the proton and how the neighboring proton is affecting the proton you're looking at. But with 2D NMR, you can look at how the proton environment next by 2 carbon or even 3 carbon affecting the proton that you're looking at, okay? So for people who are interested in biochemistry, okay, so people nowadays, they can even use NMR to analyze protein structure. You can get a lot of information. For the high resolution NMR, you can essentially solve for the structure of these protein molecules. So for protein, it typically has the molecular weight over 50,000 grams per mole. So it's a very big molecule. You have a lot of atoms, but given the right instrument and right technique, you can actually resolve. And actually, there are a lot of people whose PhD are dedicated to the study of different kind of protein using NMR. So of course, there's more electronic side of NMR and more of an analytical side of NMR in terms of developing next generation technique. Okay, so Woodward pioneered using IR and NMR to solve a lot of structure of natural product and actually confirm we can use very complicated total synthesis to synthesize the naturally occurring compound. It's because if you want to extract a tiny amount of molecule of interest from a mixture, that's generally very difficult and inefficient. So people try to use organic chemistry to assess these potentially interesting molecules. Okay, so having established IR and NMR as a main technique is used, I also want to mention you can run phosphorus NMR because it has an odd number, right? So depending on where the phosphorus atom is located, you're gonna get a different chemical shift. So it will indicate what it is. Of course, there's fluorine NMR, okay? It tells you where this fluorine atom is located, and then how far away it is from another fluorine atoms. After that, another important technique would be determining its molecular weight, mass spectrometry, okay? So remember in the nuclear chemistry, people were dealing with radiation coming from chemical substance, right? And in electrochemistry, we can manipulate electrons, right? So there are instruments where we have what we call an ionization source. So basically, we can generate a stream of electrons and manipulate such electron and use it to treat our chemical compound. So what will happen when an organic compound hit it by an electron? So you can hit it with an electron beam, so we can ionize our compound by forcing the electron out of its valence shell. And then you end up with a charged species. And we know from physics, electromagnetic, we can use magnetic field to manipulate something that is charged, right? So by controlling your magnetic field, we can separate these charged species by its molecular weight, right? So generally, you will get a loop. So these are all coil, and then that you can control the magnetic. So you can control the magnetic field and its strength, okay, and select for ion of certain molecular weight. So here, once you have your, you inject your sample here, it goes through this separation loop, then you have your detector here. And we will end up getting spectrum looking like, here will be what we call the M to Z ratio. Okay, so this is basically the molecular weight. You will get a peak of molecular ion. It's what your compound will look like when it first gets ionized. But most of compound will undergo what we call fragmentation. So if you look at this compound, because this is the very high energy intermediate, okay, so under a certain time scale, it will undergo fragmentation. So what is fragmentation? It basically means this bond broke. You end up with a carbon with some H3 around it. So that's why you will get peaks at lower molecular weight. So by looking at each fragment, for example, when I just do that fragmentation on that CH3, you will get a difference in its molecular weight. Okay, so by analyzing the mass spectrum, we can get an idea of what our compound might look like based on its fragmentation pattern. For example, if I'm losing a benzene, that would be what? About 78, 76, 78, right? Depending on how many hydrogen you have left. Okay, so with a powerful tool like this, we can get an exact formula mass. Okay, so because we know what our compound look like, right? And then we can figure it out whether we successfully made our compound or not. And then there's a lot of research going to mass spectrometry and trying to make it more portable. I'm not sure if at the airport you saw that people will use a small pad of cotton and to pat you down and before inserting into a machine to test for potential drug trafficking, right? So mass spec is a very sensitive technique. Even with nanogram of material, of a tiny little powder, okay? As long as it can be ionized, as long as the detector can detect these ions, okay? And based on its fragmentation, the border control, they can easily track down whether someone has interacted with drug, right? Like cocaine, because they will have very distinct fragmentation pattern. And of course, these instruments are carefully calibrated, so you can make sure your M to Z ratio obtained is correct, okay? So having established the three main techniques, another technique I want to mention is called elemental analysis. So there are ways that you can calculate the percentage of each element by decomposing the compound. So for a structure like this, we have C4, chlorine, and the rest is H. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if we do elemental analysis, it will give us a relative percentage. That's another way to confirm the identity of our compound. So essentially, you need 2 to 3 techniques unless for your new compound, unless this is something people already made before. Okay, so generally NMR and mass spec are required. If you enter an organic lab, these are the basic techniques that you need to be familiar with. Okay, now let's talk about separating mixtures. If the substance boiling point are different by a lot and they would not form complex, we can do distillation. We can also rely on solubility because we can do what we call recrystallization. If you have compound that display difference in their solubility, so you can do crystallization. You can lower the temperature and induce its crystallization, right? But sometimes it co-crystallizes. So in drug manufacturing, the crystal structure will affect the bioavailability of your molecules, okay? So people spend a lot of time trying to perfect this. But for separation, it depending on the chemistry you do, okay? Some chemistry, you can do recrystallization and just get rid of all the rest of oily contaminant or the side product that you don't want. But a lot of time, life isn't that easy, okay? So we will take advantage of solubility and polarity, okay? So this comes from its chemical composition, right? Okay, so from earlier chapter, we know polar likes polar compound, likes, right? And the nonpolar compound prefer nonpolar compound, right? Because they're interactive energy. Okay, so if we take advantage of its solubility difference and polarity difference, that gives us an additional dimension to separate our compound, right? So Column chromatography is another important field in organic and analytical chemistry. Of course, when we are dealing with absorption and desorption from a surface, that is physics, okay? So column chromatography, there are many kinds of column chromatography. Generally, the commonly used is silica gel column chromatography. So these are silica particles that have a size about 40 to 60 micrometer. And depending on how the silica particle is made, they could be perfectly spherical or they could be irregularly shaped. That will affect its separation capability. Okay, so when we have compound with different polarity, at the surface of this silica particle, it's a lot of OH group. So these OH group are polar, so they can interact with more polar compound. And of course, it also has to do with the solubility of your compound. Because in the column chromatography, we will use what's so-called stationary phase. Okay, this doesn't move, okay? And mobile phase. So these are organic solvents, generally, okay. So these doesn't move, but when you have a mobile phase that's flowing through the surface of these silica particles, the reason why we use these micron-sized particles is they offer a higher surface area. Okay, so it's a competition between molecule being dissolved in mobile phase and move with the mobile phase versus its interaction with this silica gel. So we can tune the polarity of your mobile phase by mixing miscible solvents with different polarity. For example, hexanes and ethyl acetate. For example, dichloromethane with methanol. So you can tune how polar your mobile phase, and that will affect how fast your compound will move. Before we actually run a column, we will do something called thin layer chromatography. Okay, so our mobile phase, to run such thin layer chromatography, it's by capillary force. It will absorb your solvent and start carrying your substance up. For a very polar mobile phase, the compound of interest will move with your solvent by capillary forces. So we will say it moves with the solvent front. As the solvent moves, elute, it will move with it. Okay, so when my mobile phase is not that polar, it may end up here, or then it won't move at all. So based on their compound solubility and polarity difference, we can use column chromatography to separate your compound. Okay, so they will elute at different time or different amount of solvent that you're adding. Okay, so and a lot of times hear what people call a normal silica gel, okay? Then you also hear about reverse. Okay, so what is reverse silica? Reverse silica are the ones that are surface modified. You can modify it with silane with different amount of alkyl chain. Depending on the chain length, you will have different polarity. The longer it is, the more nonpolar it is. So the condition will be exactly opposite than here. If it's normal silica gel, polar compound moves slower. But for reverse phase silica, polar compound moves faster because it has minimal interaction with your stationary phase. Okay, so for protein and a lot of polar compounds, sugar, reverse phase is used. Okay, because otherwise it will just stick to your silica gel and not move at all, or you won't have any resolution. Okay, so of course, there's other type of surface modified silica. So you can get amine, you can get alcohol group, you can get cyanyl group. Really what it does is you're controlling the polarity of your stationary phase, okay, because there's only so many choice of solvent that you can use. With column chromatography, you can really separate your compound, and once you separate it, then you can isolate it and send it for characterization by mass spec and NMR. Okay, so having talked about column chromatography, right? So there's another technique, but the principle is the same. It's called high pressure liquid chromatography. We know the pressure will change the flow rate, right? So you can accelerate your purification process, and also it will change the solubility, right? So you have additional control over the separation process. So similarly, you can also do something called gas chromatography. That is, assume your compound is volatile. Instead of using solvent, you're using an inert gas as a carrier, and it can, once you vaporize your compound of interest, it will go into a capillary tube, that means a very thin tubing, right? And then that has stationary phase on it. It has silica, or it can have different type of material inside. It's a matter of whether your compound want to absorb to the stationary phase or not. You will end up with gas chromatography. You will get these peaks at different time, indicating how long it has interact, or how does your compound like the stationary phase. If it likes the stationary phase, it come out later. Okay, so for liquid chromatography and gas chromatography, these are a subfield of its own. Okay, so it's possible that you can get a degree and make a life living based on your knowledge of these chromatography, because there are a lot of mixture to be separated. And then in liquid chromatography, you can also get a spectrum similar to this. So for more advanced or a more well-equipped laboratory, what people normally do would couple a HPLC or GC gas chromatography with NMR. Oh, no, sorry, not NMR, mass spec. So you can know exactly what this molecular weight is. Sorry, I made a mistake, because NMR is much more expensive than a mass spec. Okay, so just to put that into perspective, a typical mass spec is around 1 to 3 million NTD. Okay, for an NMR, it can go up to 15 million. Okay, so that's a huge difference in their price. So if you couple that, you can know exactly what the molecular weight is. And of course, there are different kind of mass spec out there depending on its ionization mode. Okay, so the power of an ionization will affect what the spectra look like. And also the resolution. So typically, how many decimal point do you want to get? 2 decimal point or 4 decimal point? That will lead to a huge difference in their price. Okay, so I think I introduced you to what you would encounter in doing organic chemistry experiments, and some basic analytical chemistry concept in terms of purification and characterization of organic compounds. So if you have any questions, feel free to ask me after this class.